Okay, first things, some.
So you're not sharing screen, sir.
No, I'll.
Okay, sure.
Okay. So we are here. Excuse me. Yeah. See, next week I have some commitments. Okay, that will keep me away on the 20th as well as the 24th. Okay. So I'm proposing that So I want to have classes on 21st, 22nd, and 23rd. Okay. Is that okay?
It's fine by me, but I think Devjit had a clash on at 3:30 on Tuesday and Thursday, so we'll have to find a new time. I
I'm
think.
flexible with any time. Okay. So why don't you? Hi, Madhukar. Hello. Yeah, I was just telling the class that next week, 20th and 24th, I will not be in. So 21st, 22nd, and 23rd. So 2 of those days you will present the students' presentation on the topics. One other day we will keep it open. It could be either some open-ended things, some new abstraction techniques. It could be devoted to general discussions or a project discussion. Okay, so that's what I'm proposing. 21st, 22nd, we'll have your presentations, and 23rd. So we can agree on a time. Okay. So Wednesday, it's the usual. So on Wednesday, we can have it at 3:30. It's for 21st and 23rd. We'll have to come up with a mutually suitable time. Can we decide now, or we will decide by email?
So on Tuesday, I have a class at. No, actually, we don't have that class. That course finished. So yeah, Tuesday I'm free. Thursday, 11:50 I have a class. Other than that, I have no class.
Yeah, how about if I proposed 3:30 on 21st and 23rd?
No, I think Sir Devjit has a class on 3:30 at 3:30 on Tuesday and Thursday.
Tuesday and Thursday. Okay, so that is out. Then if it's not at 3:30, then it has to be either 11:30 or something. 11:30.
11:30 works for me on Tuesday, but not on Thursday.
Okay. 11:30 on Tuesday. And, so earlier would be better then? It's 10:30.
Yeah, that's fine by me. 10:30 is fine.
10:30. Also 10:30 ours class tends to go for 15 minutes. So then it will go into 11:45. Is that okay? Is that okay? See,
yeah.
Yeah.
On Thursday, I have class at 11:50, so it should still be fine.
Okay. So how about for Madhukar and Diganta?
Yeah, it works for me.
Fine.
So Wednesday at 3:30, Tuesday, Thursday at 11:30. No,
10:30.
10:30. 10:30.
I think Devjit is also here.
Yeah, Devjit is here. So Devjit, we are discussing.
Yeah, sorry, sir. Like I had some internet connectivity problem.
That's okay.
Yeah.
Yes. Next week, which will be the last week of scheduled classes, we'll have 3 lectures, 2 of which, and I'm requesting for a change. Okay, says I will be busy on Monday and 20th and 24th. So we propose that we will meet on 21st, 22nd, and 23rd. The 21st and 23rd, we will start at 10:30 the class. Is that okay with you?
Sir, 23rd I have like a exam. So if we
what
can,
time is the exam?
I mean, it's at 3, but like I have to like study a little bit for that.
Yeah. So how about then on Thursday after the exam?
Yeah, that will work. Yes. So exam
That will
like,
exam will be go till 5 o'clock.
oh, okay. So is there a upper limit for when we can
For
start?
me, it's not okay. For all of
Okay.
us is
So my exam will go on till like probably 6:30, because 3 to 6, and like there might be like half an hour more because he usually gives us half an hour more.
okay. So then, since then it will be
Or like 10:30 is fine too. That should work.
yeah. I think 21st and 22nd will be your presentations. Okay.
Okay.
23rd will be just open discussion and project discussion and open things. Yeah.
Okay, that will work. Yeah.
Or we could have both on Wednesday. So one at 3:30, one in the morning.
Yeah, I mean, like I'm fine with it, but like I mean, 10:30 on 23rd is also fine with me. So
Oh, 10:30, 20. Oh, but
yeah, that is fine. Yeah,
it will not come in the way of your preparation.
no.
Okay,
It's
so
fine.
then 10:30, and then 22nd is 3:30. Okay. Now, there will not be any class. Now, some of you were asking for extension for the project. How about if we extend it till 7?
Yeah, that should work. That is fine by me.
Yeah, we need to meet once during that week for you to kind of present, all three of you.
Yeah, we can do that in that week, the week after the end sems.
So fine. Then. So we will decide on that. Next week. Yeah, today, yes, we were in the last class, we were discussing, we had, yes, Diganta had described what, and defined, described the expectation for task 2 was, what it was, the statement, as well as, this is primarily, you would explore a verification for the LSTM system using the unrolling method. Okay. Now, last time when we met, okay. So any questions on what your expectation for task 1 is? That's clear now. So there, what you're required to give is just a complete formalization of these 2 properties. Just it's a pencil and paper exercise, but a complete definition. Yeah, that's what is expected here. In task 2, you will have to check, and you'll be focusing on the cycle property only, not the quotation property, for the rest of the tasks. Now, you will try to prove this cycle property by unrolling for some small unrollings. Okay, that is task 2. Now, that will require you to actually make copies of the actual system. When you unroll, it will make copies of 1 copy of DNN for each iteration. So since you were having issues, complexity issues, and you have to feed it to Z3. So
yes, sir. So I think removing the variables actually fix those issues. So I did get a.
Yeah. I want to hear from you what the latest on that. Okay. So
yeah. So like last time, it actually didn't give anything, right? Like I had said, I had given it.
yeah.
It did not come back. But like after removing the variables, actually its complexity decreased a lot. Like in 5-10 minutes, it gave like it was able to output something. But there are still some weird things happening. Like suppose if I don't specify the
No, no, go
input,
ahead.
and if I only, huh?
No, go ahead.
You
So,
were saying?
nothing. Yeah.
Yeah. So if I don't specify the input word like input letter, and if I only give it H and C, then for some reason it's giving me unknown, which I haven't able to figure out why. Because Z3 is so I'm still doing the same thing where I'm keeping the output where I basically just want the function, want the model to give me an output. So so just giving it a fixed input, it is able to give me an output. And I checked with the model also, so it's giving me correct output.
What do the inputs range over?
So there are basically 58 characters, I think. So and each are one hot encoding of. So they're vectors of length 58 with ones and zeros. Only one where it is. So basically,
Yeah, but
Yeah, I
why
fixed-
give it, at least try giving it some concept, because it's one hot encoding.
Yeah.
There are some real constraints on what legal inputs are. Huh?
yeah, but so if I give it the constraint, so if I give it the constraints also, for some reason Z3 was not able to give me a solution. But if I give it exactly give it a fixed input. Suppose if I set the 46 thing to 1 and the rest to 0, only then it is actually giving me something, which I haven't
see
been
that-
able to figure out why.
The way it's
But-
not surprising when you give specific inputs, it is the most constrained now, so it can somehow propagate each of those.
Yeah, but Z3, like Z3 was giving unknown, which I haven't seen before. So unknown is like it's probably not able to decide anything.
But that's
So if it
coming
if
from
it was-
linearity also, I think.
so if it was stuck in a loop, then it would. I mean, if it was stuck and not giving anything, then it would be different. But yeah, since it's giving unknown, I'm not sure why that's happening. But at least so far, if I fix the input, then it is able to give something. So it's much better than the previous attempt. So it is.
But did you try for, this is all for one copy, no?
Yeah. So I haven't tried yet more than this. I will try that soon. So I've just tried up to here. But yeah, I think Z3 should work with some tweaks.
Yeah, but I think, see, I mean, this is better than, some movement, but I'm not sure, okay, since here, I mean, AS3 involves only one thing, at least for what you also need to experiment with the linear approximations that Digant discussed and wanted you to try. Okay, if it doesn't work for, obviously, if you want to verify some properties in a meaningful fashion, it has to be done for arbitrary inputs, no? So if on inputs are not working.
No. So there is one thing that I've just now tried, which is basically, so like Diganta was saying, from H and C, you can get an input using that output DNN. So like given an arbitrary H and C, I am trying to basically fix X that way, like fix the input that way, saying now the input is the DNN. I don't know if it will work, but the DNN output of H and basically it's the DNN output of H, and then we'll see if it's able to give me something. It's running right now. I'll let you know if it gives something useful.
How are the other two people contributing? Because you guys are very silent. You're helping Ame out?
No, sir, not really. I
So
have
you
not.
To divvy up the work somehow, okay? So maybe for task here, for example, task 1, there is not much. I mean, it is appearing to me that at least in terms of actual doing it with Z3, etc., that Ame is taking the lead. Okay, but even
Yes,
task
sir. Yeah.
2, there is something that the rest of the two of you can help out with, and that is to try.
No, so we'll do the cycling property and
No,
we'll
no.
explore that.
Yeah, that is for formalization, you're saying, huh?
Oh yeah.
No,
I mean, like,
formalization
we
is
have to-
just pencil and paper. That I think you can do. So that is like
Yes,
that is.
and
So even for task 2, what I'm suggesting for you to get warmed up, what I'm suggesting that you can do is try the linearization. Okay.
okay.
After you linearize the things by
How Diganta said, yeah.
by then what you're doing is, if you specify constraints on the outputs of the F gate, I gate, G gate, and O gate, then you can also then put some bounds on all the multiplications. Yeah. After that, you should be able to ship it to ReluPlex. Okay.
Yeah.
Now, that experiment, start with a small problem and use ReluPlex on it. Have you already done that as part of any of the assignments, or you never used ReluPlex, correct?
No. So
No,
there
sir, we
is
have
like,
never used ReluPlex.
Yeah, I think what you can do is while Ameya is experimenting, pushing Z3 in the ways that we have discussed, okay? What you can do is to install ReluPlex and start with a small problem, and with this after this linearization, let's call this network N. Okay.
so
Now,
there still will be like multiplicative things, right?
N will have multiplicative thing, okay, in which Z3 is.
Yeah.
But what I'm asking you to do is to come up with an N prime, which will eliminate those multiplicative things, so that it will reduce into a linear approximation
Yeah.
of that. Okay. Now, if you're only doing it for specific constraints on F, I, G, and O, it will also be not a complete over approximation, but for some slice, okay? For some slice of thing, like if you assume that the output of F is greater than or equal to 0, then there'll always also be a case where it is less than 0, correct? So you can even start with trying for some such cases, and then see if some properties get verified with ReluPlex. Okay.
Yeah, so some sort of an approximation which will help us.
Yeah,
do that.
that's right. So that, whether that will be a complete approximation, complete in the sense it handles all the cases that you assume for the bounds on the output that you might get with F, I, and G. So basically that will mean, correct me if I'm wrong, Diganta. So with that linearization, they can completely replace this box F, I, G, and O with those constraints, correct?
Yeah. So I was thinking only on Fi and O, but yeah, they can completely replace those blocks.
Oh, okay, whatever. No,
Yeah.
yeah. But see, this part is not, by the way, F, I, and G, O themselves are not producing any non-linearity, okay? At the output, it's only when you do the multiplication, after that you're getting it, no?
Yeah. But if we put bounds on Fi and O, as we saw last time, that will actually allow us to replace the multiplication with two linear.
No, but that I understand. But then you will have to do that for all of them, no?
Yeah, for Fi and O, yeah.
Fi and
O. So we only need to bound one input of each star node. So Fi and O.
One of them. Okay.
Yeah.
Is that clear? So that is what I want the other two of you to be doing. Okay. Then now,
Okay.
yes. If you have any doubts, you'll have to ask. Yeah. Yes, there was some sound by somebody.
No, I said okay.
Yeah, I think what you should do is if there are any, see, last time, Diganta, you said that you would give some details as to how they could download, install Reluplex. Can you do it offline, or you want to add some?
Yeah, I can do that offline. So yeah, I'll just upload like a text document to the Google thing.
Yeah, okay.
Yeah, if people want, I can also do it like do a demo. But yeah, I mean, I have not prepared anything, but I can just go and show you and download and like, show you how to do that. Yeah.
I mean, like, I just have one question. I hope we don't have to compile it from the source.
No, there are binaries. They have their binaries on GitHub.
Oh, that's nice.
Yeah. But even if you do, I think I did build. It's not a big build.
Yeah, I mean, like, or whenever I try to compile something, always something or the other fails.
I mean, it will initially, but yeah.
No, this is happening for like 4 or 5 years. Every time I try to compile something, it always fails.
I see. Okay. Yeah, but they have binaries. At least for Linux, they do. I'll check. If they don't have for Windows, we'll figure something out. Okay.
Okay.
Yeah.
Actually, I don't use Windows. Like,
Okay, sure.
So, like,
so then I think it should be fine. I'll just check.
Okay. Thanks.
Yeah, what would be a good small example that they could try Reluplex on, just as a test case before they plunge into checking some properties for the linearized version of
Yeah, I think this example from the paper, the Reluplex paper, had this DNN with only 4 nodes, right? I think that is a good thing to.
Yeah, I think that's the one that Madhukar slides also has.
Yeah, exactly. Yeah.
Yeah, and I'm sure when you do linearization, there will be some questions that you guys, I mean, you will have to start doing it on paper, and then, I'm sure you will hit some roadblocks, which you could get clarified, by emails, consultation with Diganta. Okay. So I'm assuming that the Harsh and Devjit will do that and give us some feedback by next Tuesday. Yeah.
Yes, sir. Sure.
Okay, so that will be part of the thing. So now today, what we're going to be, I'll be talking about a little bit more detail is something about verifying without enrolling. Madhukar has already covered but the one that I'm going to be adding is invariant inference, okay, which is part of what you will be doing in some limited ways. Okay, let's see how far we progress. At least some, it'll be good for you to do. So that is one thing extra that I'll be covering. All, most of what we talk here is there in chapters 5 and 6 of the paper, that part which was not covered in full detail. Certainly chapter 6, some parts of section 5 and 6, but I think most of it you should be able to gather from here. Okay. First, I will talk about a little bit of general thing as to what it means to verify using an invariant, which is somewhat overlapped with what Madhukar has already covered. And then I'll get to invariants, and in the process giving some details that are specific to this particular LSTM example. And then after that, Diganta will give more details on specifically the kind of invariance, the shape of invariance that we want you to explore for LSTM specifically, and what you can do. Now, I know the task 3 is the scope can be very big, but even if you can do some small part of it, which will be defined in this, during the course of this lecture, it'll be good. Yeah. So you can read this. I can make this a little bit bigger. Oh, I don't know. Is this big enough? Or you want it bigger?
It's okay for me.
Yeah, it's visible, I think.
Okay, let me keep it this. Yeah, so what is in task 3 in explores verifying without unrolling, okay? Verifying without unrolling, as Madhukas already pointed out, requires you to get an inductive invariant, okay? And what it really means is that you will only, the advantage of verifying without unrolling using inductive invariant is you will be for this, doing it on just a single copy or a slightly modified version of a single copy of single time frame of the original network. So the original network had kind of loops. There you have broken that loop, and you have the contents of the memory, which in our case will be HC, the vector HC, as an additional input. And since our invariance as well as property that we want to verify will have a time component in it, so T is also assumed to be available as an input. So and the rest of the thing will be your network as is, like it is here. Okay, so that's what I mean when I say that it is a single copy. And an invariant is essentially a condition, a constraint on the content of memory. In our case, it is HC. So and that invariant has to satisfy, for it to be an inductive invariant, has to satisfy 2 conditions, okay? It has to satisfy the initial check. So here I is the invariant. Once you propose an inductive invariant, you have to show that the initial condition implies the invariant, and then it has to satisfy the inductiveness check. It has to be inductive, which means that if you start with something where invariant holds good, and then you take one step as per this, then your invariant condition on T plus 1, the next memory content, the next thing holds good. Okay. Now, before I get into saying how do we generate such invariants, let me first give you, how do you check this invariant? Once you propose some invariant, how do you check the invariant? That also Madhukar discussed, and that how do you check that your proposed thing is an invariant? Okay, for example, if your invariant was something like this, in our case, there's H and C, it could be some constraint. So H is, it's usually a function of the content of the memory, because it is specifying a constraint, and it can also, the constraint can involve T. So it could be H is less than 3 times T minus 1, and C is between -5 and 5. So that could be hypothesized invariant. Okay. Then checking that it is an inductive invariant consists of two things. One is you have to do the initial check. Okay, so whatever the initial condition is, initial predicate is for your system, you have to show that if you assume that, then your invariant is true. So this init condition has to come from your LSTM system. This init, in our case, it will describe the condition after the IP generation loop, whatever the value of HC is after the IP generation loop is what I'm saying. Okay, Diganta, is that correct, or you want to add some more thing to it?
So I think I'll talk a little bit more about this later, but basically
Okay.
I was thinking that we'll just have HC as like all possible values within a bound.
Okay, so he will talk about what exactly the initial condition is for the system. So in general, there is a component where you will have to check. Okay, so notice this check here is a purely logical check, in the sense it does not involve the DNN, okay, or the feed-forward network component, N cap or N caret. Okay, it does not involve that thing at all. It's a purely logical thing because you propose something, an initial condition, which is a formula. Invariant is also something that you will propose, and so this one is a simple. This whole thing is an SMT formula, and it can be checked using SMT or Reluplex for that matter. So if both initial condition and invariance are in the linear fragment, you can use Reluplex readily. Okay. If it's non-linear, so since we will be proposing only linear invariant templates, so it is already, this can be checked using Reluplex as well. But the important point I'm making is this one itself does not involve any N cap component. Now, inductiveness check checks if by doing one step of one arbitrary, if you start from some arbitrary state that satisfies the invariant condition and you do one iteration, then your the new value that you get for the memory content and satisfies the invariant. That is, invariant is preserved, and that will of course involve N caret. Okay, so this is your invariant, and if you the output that you get by propagating those values of HC by over one time frame, you get this new content and the output. Okay, and then you have to check that the invariant condition is preserved by that new memory content. And I'm also giving the time because, as I said, the invariant can involve, it's free to use the time as part of it. Okay. So, and caret will be, in your case, something like this, where F is the accumulated function that is implemented for transforming the current memory content into the new memory content. Okay, that's what does. So in general, N caret also not only transforms the transform HC, it also gives the new output, and that's why there are two components to it. Okay. So given this, this is the condition that you have to check the validity. So you have to check this validity, which means for all H, C, and T that this thing holds good. Okay. So this will of course involve a model, a formula denoting N caret. So what is the in order to check this using either Z3 or ReluPlex, what is the query that you have to send to an SMT, say Z3? Okay, Harsh, can you answer?
Yes, sir.
Yes. What is it?
This particular query, like for checking the invariant, like we just have to use that n, whatever that previous thing that you have written, I think.
Yes, this one. Yeah.
Yeah.
The exact query. So in order to check the validity of this thing,
Hmm.
you have to check take the negation and then check. Okay. So
Yes, yes.
yeah, that's what I was, specifically the query that you will be sending is whenever you have to check that something
Negation, and then it is unsat.
you assume invariant and you have the next input with the equality, then you conjoin that with the negation of the invariant in the next over the new inputs, I mean the new outputs, okay? And that's what you will send as query, okay? So that's the distinction that I'm making. And then if that is unsat, you're done, okay? If it comes out sat, then you have to propose your inductiveness check has failed, okay?
Correct.
So that is the level of detail, although sometimes I'll just, keep saying inductiveness check, but what you actually have to send to Z3 or ReluPlex will be, that's what is usually meant when one uses a query to be sent to SMT. Yeah?
Yep.
Okay, so at the end, Diganta will give some templates that you can actually use for this particular system, and then you can actually check them, okay? Once you have either the linearized version of it, and then you can use ReluPlex, or the non-linearized version that Ameya is experimenting with, and you can actually check, using Z3. Okay, so then the question is, next is, how do you get automatically infer an invariant? See, either you can use the manual approach, where you will propose something, or you can do some automatic inference. So as part of task 3, not only will you be, that's the part where you propose a specific invariant and then checking, you can say that can be considered as part of task 2, and invariant inference is part of task 3, okay, whichever you want to split. But a big part of task 3 is asking you to kind of experiment in invariant inference, okay? And the method that you will be using is what I'll be describing, okay? And Diganta will add some details as to what we want you to explore specifically for the LSTM system. So what the method that you use, I'll get to this in general. This thing is undecidable. I'll get to this discussion later on. So one method that, the method that we'll be using is what can be called as guess, check, and refine in a loop. Madhukar also mentioned briefly in his lecture this method. So guess means you will propose some invariant that sticks that uses a certain template. Okay, template is like the shape of your invariant, okay, and which has some parameters, and then you will check by generating a query, which I've already described how you check. Checking means really checking the inductiveness check, okay, and if it succeeds, then you have something. Okay, then you already have an invariant that belongs to that template. Otherwise, you will have to refine it you will have to refine by refining some of the parameters. These templates that we'll be using will be parameterized with respect to a bunch of parameters. Okay. See, in the paper, the template that the authors use for the invariance is exactly like this. Okay. So the contents of memory is less than or equal to some alpha, which is in their case is just the coefficient, okay, which is a number, times t minus 1, and alpha is the parameter. So then the problem of invariant inference reduces to what is the most optimal alpha that you could do. So the smaller the alpha, in this case, the tighter the stronger the invariant. The looser the alpha, the weaker the invariant. Okay, and so invariant inference, once you fix the template, really is can be considered as an optimization problem of one of searching for the most optimal alpha. Okay. That is inductive. Okay, because if you see, for example, there's always an invariant. The weakest invariant is something which is completely unconstraining on memory. Of course, that won't be useful. So you have to try and get the best alpha that is able to, that is strong enough, but not, but that is adequate to prove your post condition. Okay, so you don't want to make it very unnecessarily strong. Then searching for that will be hard. So, but you don't want to make it too weak either. So you just have to be strong enough to do it. Okay, so that's why. So while you search this refine loop, each time when you get guess a candidate, and if it is an inductive invariant, you check if the post condition, the post property, you can verify it. If you can, then your search is done. Okay. Otherwise, you refine it by trying to pick a better alpha. Okay. For the parameter, and that's what this thing is meant to do. Okay, so you can use more general templates. Okay, so let's see. So I'm also looking at the time. So so the step 2, so there, I mean, I'm just giving you an example here. So you can use interval templates. Okay, which means that it has bounds on each the memory component. In our case, there's H and C, so you can have an invariant of this shape. Okay, this is called interval because there's an interval for each component in your memory value. So in which case the parameters will be the lower and upper bounds of so of the interval, or you can even have more sophisticated thing where H minus C is doing and so on. So, but each the important thing to notice here is a template will not only give a shape, but it will also define a set of parameters. It's the parameters that you will have to optimize over to get a tight enough invariant that satisfies your that meets the purpose. Okay. Yeah. So there is a general method that you can use. Once you fix a template with parameters, then if these parameters can be one method, okay, what is the search method that you use to get to the best possible value? One method can be it relies on kind of a total ordering on this parameter, okay? And you do what is called a binary search on the parameter to get the the tightest parameter, okay? The smallest parameter in that ordering, okay? And that you can do using a binary search strategy, okay? And that's what is described here. Just for you to get familiarized. So, where is the algorithm? Right here. So here, this is for the template shaped this way. So where the parameters is of any questions up to this point regarding either the way that you do invariance check, I mean that, or the general scheme for what a template means, what is a parameter is, and what the search method is.
Yes, sir, it's clear.
Okay. See, the point once again I'll emphasize is there are several possible candidates for invariant. Okay, and you want to get the something that is indeed an inductive invariant, but that is good enough to prove your property. And what this invariant inference does is, given a template, it tries to pick the one that is strong enough to prove. It starts from the weakest candidate and then gradually tightens the bound to get to the stronger and stronger candidate invariance. So now, started. Okay. So so there is this question that you can raise: what is the strongest candidate? Okay. Okay. So the strongest candidate invariant is the one that that the actual is something that characterizes precisely the possible values that the memory, the content of memory can take over the course of all iterations. Okay. Now, computing the strongest, the most precise invariant it really boils down to, it must include the all the values that satisfy the initial condition. It must include, if you start from that, then all the values that you get after doing one iteration, which in this case is one time iteration and 2-time iteration, and so on and so forth, until you have accumulated all the values. Okay, that is the strongest candidate. Okay, so if you could compute that, so what we're looking for is, when I propose something like this is what I call as a closed form representation or a symbolic representation of the invariant. What I'm looking for is the strongest one will be precisely something. It will be a predicate that will characterize, include exactly the value. Now, getting to that is very hard. It is not only complex, in general, that's what is makes this problem, one of the reasons it makes it undecidable, okay? Especially over an infinite domain. So what we do is, that is not only not decidable in all cases, even in cases where it is decidable, it's not practical. And therefore, you try to get something which is still an inductive invariant, but approximations, over approximation of of this, and that's what this thing is doing. Okay, and so it's in that sense. Since I mentioned this, I will make it complete. So this is in general undecidable. Okay, even when undecidable, it's hard. So there is a case for which it is always theoretically decidable. So for if your domain, that is the domains over which H and C range over, and if you limit your time to a fixed bound, I say that the domain over which the invariant is defined is finite, then it's always decidable. Why? Anyone would guess? Devjit?
Because you can always brute force.
Yeah, no. But why is it that you can always do a brute force? Because after all, this invariant inference is a search for some I that satisfies the inductive invariant. If that I is a predicate, okay? If that predicate is the set of predicates, if your domain is infinite, the set of predicates over the domain is also infinite, okay? How can you check? Okay, so that's why it is in general undecidable. So, but if it's finite, the possible Boolean functions or predicates are Boolean functions over that. Okay, the number of Boolean functions over a finite domain is always finite.
Yes,
So
and you can just try all of them.
Yeah, that's what probably you meant. You can actually enumerate all the invariants in some order. Okay, and then you will find something. So which will work, or if not, you will keep looking for something. So that procedure is always bound to terminate. And that's why for finite domain, it is decidable. I mean, even for that, how do you make it, because the number will be so huge that you need to be very clever about it, okay? But in general, certainly if it is infinite, then it is not decidable, okay? Because there are an infinite possible number of predicates. But even for finite domain, it's hard. So there is reasonable methods that can search and produce some decent results using by restricting the templates, using heuristics, and even using machine learning. And what we are doing here is fixing some templates and then asking you to use a specific method to search for that. Okay, let's see, given the time, etc., how much do you have? Since binary search is really doing, this is what it is doing. Okay, so here it is searching for the best alpha. Okay, a single parameter alpha here, which is being used, and the template is this, which I've already shown you. And the alpha is assuming that the alpha, the parameter itself, the value for the parameter here, which is a coefficient, is ranging between some least value minus m to some maximum value m, for some m large constant. And then what it does is it does a binary search. Okay, so given minus m and plus m, it generates the midpoint in that range. Okay, so the possible values that alpha can take is that I told you it's a total order. Okay, this is one way to do. There could be several ways. So between minus m and plus m, and then it'll take the midpoint, and then it'll propose that as an inductive invariant, and it'll do the inductiveness check. Phi I is actually the query. Okay, the inductiveness check query that I showed you. So it'll check if it is unsat. If it is unsat, then you know that you have an inductive invariant. Then it constructs the query corresponding to doing the post check using that invariant that it has proposed as a candidate. And if the post check also succeeds, then you know that you're done. Your property holds, then it returns. No need to refine it, okay? No need to refine, do the refinement. If not, then you'll have to, then if that doesn't succeed, then what you have is, although you have an inductive invariant, you do not have, that's not adequate, okay? That is not, that is too weak to prove your post property. Then you have to look for a better, in the sense, a tighter parameter, okay? That gives you a stronger, that is, a tighter constraint, for the invariant. And that's when you will look at either, move the midpoint, okay, to that, you change the extremities, which started with minus m and m, to your midpoint. This is the classical binary search on the possible values that alpha can take, okay? Then you set it to either change the upper bound and look at the lower portion, or the upper bound, okay, depending upon which way it is. And And sometimes here you can use the counterexample also. Okay, so this is roughly how you guide your search until you say the step that you can use to increment your alpha by can also be set. Okay, and you can go up to a certain point and then do it. So this is just picking picking tighter and tighter, smaller and smaller value of alpha, and the way that you do is can be through binary check. Okay, so that is one method. Now, what Diganta will do is how you will the kind of invariant that we want you to explore, the template that we want you to use, and a particular search method that we want you to explore, okay, for searching for the invariant. So before I hand the mic over to Diganta, who will explain that. Any question on this general method, the general scheme that I proposed? I mean, that I described.
No, but like again, so how do you know that the invariants will be only of the form h less than alpha into t minus 1?
No.
How?
Whether that an invariant that stick to
I
a
mean,
particular shape will work for
haha.
you is always an open question. But all
Yeah.
it does is, once hoping that you're limiting your search to some invariant that fits that
Structure.
shape, you're trying to do the best, the most optimal one. Okay, that's all this thing does.
Okay.
So there's no guarantee. So there's no guarantee here that there is a guarantee that you can find some inductive invariant if you search long enough. Whether that will be adequate for you to prove the property, which in our case is a cycle property, is an open question. Okay, so your ultimate whether the task 3 has a lot of uncertainties. Okay, whether you will be able to, I'm hoping that at least you'll be able to find implement task 3. You'll make enough progress to at least discover some invariants, inductive invariants, but whether it will be strong enough to prove the property or not, we don't know. Okay, so yeah. So does that answer your question?
Yes, sir. Yeah.
Yeah. But in order to make the task prescriptive enough so that you can implement something within the time frame that we have, we are proposing specific templates and a specific method for you to do the search. Okay, and it is unclear that it will be good enough to prove the property, but maybe you have discovered some inductive invariants using the method which you would have checked and then successfully. Yeah. So that's a hope, and in the process, I hope that you would have, we all would have learned something. Yeah. Okay. So Diganta, I will stop sharing and. Yeah, that's why I put task 4 as first. Task 3 is just generating some invariant, okay, with the methods, and then checking if it is an inductive invariant. And then the task 4 is see if some generated invariant really is useful in proving the property.
Yeah. So, okay. So as Sarv was saying, so I'm going to talk about what these templates are, or at least what, sort of I thought that we thought that we can use these templates. What kind of templates you can use. So in general, as Sarv was saying, the invariant space, the space of all possible invariants. See, our domain is in some sense infinite, right? So the space of all possible invariants, this is actually going to be infinite, right? So any search technique that you have, anything that searches for an invariant can only search a finite chunk of this. Or you'll have to live with the fact that your search can go on indefinitely. And even then, usually you can only still search a small chunk of this. So, so at the end of the day, we have to somehow carve out a chunk of this and settle for some subset of this, so some subset space S of all of these in space of ins. And we have to sort of be happy with searching for invariant only in this space. And of course, there is always this possibility that or that we cannot find an invariant in this space that actually gives us the proof that we're hoping for. But this is something that we have to unfortunately deal with when we have infinite domains, because in general things are undecidable. If you could always do it, then it wouldn't be undecidable, right? So what happens, or what things boil down to is, it boils down to this carving out of this subspace, right? So choosing this subspace becomes somewhat important, or something that is kind of central to how well your technique performs, right? And as you may imagine, there is no really very strict science of choosing this subspace. It's all intuition and heuristics in most cases, at least from what I've seen. And you have to sort of use your knowledge of the specific system that you're working with to help you. So basically I'm going to talk about one such subspace or template of invariance that we are going to look at. So when I say template, what I mean is basically it's going to have a bunch of parameters. So for example, this is a template, right? So we have, or say we have C is one memory cell, right? So so if you have something like, say, or sorry, T minus 1. Yeah, so then this can be one template where alpha is a parameter. Hello?
Yeah, something happened.
Can you see my screen?
Yes. Can everybody else see it?
Was my screen not visible all this while?
No. Momentarily.
No, it was visible.
Okay.
That's
No,
all.
I think I had dropped off and then I joined back.
Oh, no, but why should that affect the rest?
I don't know, but that.
Yeah. Yeah, so in any case, this alpha is going to be a parameter, right? So then basically by fixing an invariant of this form, what we are saying is that this subspace is going to be the space of all invariants, where alpha is a parameter. So we are going to say that alpha belongs to some domain, right? And this thing, we call this a template. So in some sense, this template is basically a subspace that is going to be parameterized by a bunch of parameters. So here there's only one parameter. In general, it's going to be a subspace where a bunch of parameters is going to give you an invariant. So you're going to have an invariant that is in some sense going to be parameterized by alpha 1, alpha 2, and so on, a bunch of such parameters, right? So this is the space that we're going to search for. And then the search basically begins to boil down to finding alpha. So what I'm going to describe is this template, or how do you actually take this, express an invariant in terms of these parameters. And I'm going to describe one such way of doing this for this particular LSTM model that we have. Whether this is good or bad, we'll only be able to tell once we have tried it out in some sense.
Yeah, but I think, see, if you allow for, there has to be something. Go back to your picture that you wrote to your board. Yeah, the question is, of course, if you're in an infinite domain space, the alpha could be minus infinity to plus infinity. You never know. Okay?
Of course.
But the hope is that you're not. Okay, there is some finite space. So, in this case, some minus m to plus m, where m is some constant, within which you can find something, okay, which will be good enough. Okay, because after all, if the property is, that you're verifying requires, and if your system is such that the output it produces is between those values, then hopefully there is an inductive invariant. There is an invariant predicate within that for an alpha within that finite range for which it is inductive, and it may be useful. Okay, and I think that is not unreasonable to expect. Okay, for realistic system. So this is not. While it is very hard, and I think the situation may not be as hopeless as it might seem. Yeah. Go ahead.
Yeah. Okay, so I'll talk about this thing about like what the finite domain on alpha is going to be like a little bit later, but let's see. So let me just copy over this thing here so that I can. Yeah. So.
Yeah, by the way, I want us to go till noon. Okay, I hope it's okay for you guys. Yeah.
No problem, sir.
Yeah, 15 minutes should be enough. No, Diganta?
Yeah, sure. Yeah.
Give it
So okay, yeah. So this is going to be a template. So first of all, things are going to be so we are going to have upper and lower bounds. So a template is basically going to be based on bounding H and C by some upper and lower bounds. So you'll have some U and you'll have some L. So let's call it alpha L, and you'll have some alpha H, right? So this is going to be your template is going to be based on this having these upper and lower bounds. So essentially, all your HIs is going to be you'll have some alpha L, H, I, and or let's call this alphas and the other ones betas. That will be better. So it's a alpha Li and alpha Ui. Similarly, for CIs, you'll have some beta Li and beta Ui. Right. So what this will do is that for each iteration, in some sort, for each check, you'll end up with a bound on these guys. Right. So you'll have a bound here and a bound here. Right. Now, the other thing that I want to basically add to this invariant is I also want to, or this template is, I also want to add bounds on these things. So if you remember, we were talking about bounding these things when we're linearizing the DNN, right? So from that perspective, it makes sense to add bounds on these things when we are like creating the invariant template, because then automatically the template forces are like gives us a linearization of the LSTM network. The other motivation from behind bounding these things is that because C is the memory, it's a long-term memory, right? So we would expect there to be some sort of values in C that don't change much, or that have a certain pattern that doesn't change much, and so on, right? That is going to be guided, like whether parts of C is going to stay the same or it's going to be overwritten and so on. That is going to be primarily be guided by these gates, right? So it's going to be guided by the F gate, the I gate, especially the F and I gates, and the O gate is going to guide how we interpret C in some sense. So so these, like bounding these, makes sense because then what we're doing is we are proposing constraints on how we are changing C in each iteration. So that would hopefully allow us to, in some sense, hopefully reason about what parts of C change and doesn't change, and so on. So that is the idea behind putting bounds over here. And similarly, those bounds will also look like, okay, so I'm sorry. So those bounds will also look like something like, say, Fi is going to be, let's call this gamma Li gamma ui, and so on, right? So you'll have all of these bounds. So this is the first thing. So what are we bounding, and what does it mean to be bounding? So it means that we're going to put an upper bound and a lower bound, and what we're bounding is going to be the C's, H's, and the outputs of the Fi and O gates, right? So I want to just maybe write that down here. So the first thing is that bound C, H, F, I, and O, right? Now the second thing is that if you know that these bounds, like, or if you notice that our property has this particular T max, right? So the property, we wanted to only check our property for a maximum amount of T, right? So our property is predicated by, or it's like has an additional constraint that the time step that we have is less than some T max. So if we have some like time concept in our property, then it makes sense to have a similar time concept in the invariant, right? So we're going to introduce that into the invariant in a similar way as the paper does, by in some sense allowing a particular time value to be a part of this thing. So instead of having alpha times this, we're going to have T minus 1 times this, and so on, right? So so then basically our invariants now begin to look at bound C, H, F, I, and O by some parameter alpha times T minus 1 on each side. And this is basically going to be the structure, in some sense, of the inductive invariant that we're going to.
So which means that the invariant is a conjunction of several things. Okay, there's more things to come, is it? Okay. So there's a conjunction of some interval constraints on each of these things, okay, with some upper and lower bound parameters, and some constraints of this kind, bounds, with one alpha parameter for each C, H, F, I, and O. Correct?
No. So I'm saying this step by step in not the sense that like when I say number 2, this actually replaces number 1. So in each step I'm adding more
either
details.
Do this kind of parameters or this.
Yeah. So I'm just progressively adding more details with
given the time that they have. So you'd rather, which do you think will be more useful?
No,
number 2 might be more useful, or number 1?
I'll give a very explicit form at the end. So I'm just adding more details step by step. So this is like view version 1 in some sense. This is going to be version 2, and then I'm going to add a version 3. And then we'll try, I think, the version 3 at the that I say at the end directly. Is that okay?
Yeah.
So basically so instead of giving you the whole thing, I just wanted to show it piece by piece with some motivation behind each one of them. So right now then over here, the form that we have is of our invariant looks like this. So here we had something like alpha Li. Maybe I should use. So here we had alpha Li, C, alpha Ui, and so on, right? And similarly for H, Fi, and O, and so on.
Now, what is the I here?
So I here is
is the search method, okay? In the I iteration of the search, okay?
Yeah. No. So it is the component of the Ci vector. So it's a component-wise bound.
Yeah.
Okay.
1 for C, 1 for H, 1 for F.
Yeah, 1 for C1, C2, C3, 1 for H1, H2, H3.
There's an I. The name I is being used for a component also, and then there's index. Yeah.
Oh, okay. Maybe I should. Yeah, that was on. Yes. Okay.
Yeah.
Yeah, that was bad notation. Yeah. So here again, in version 2, what we're doing is we decided that we're going to add the time part of it in. So we're going to say T minus 1 times alpha L J Cj, and then T minus 1 times alpha Uj. Now this is okay, but there's still some other information that we want to put into the invariant in some sense. And
There
that
will
is,
be, too many parameters in this case. Now, if you're actually specifying separate constraints on each of the component, and your vector is what? How big are these CH vectors? They're
yeah, some 400-ish.
wow. So this will be 400. Okay, so the parameters then will be
Yeah, fairly big.
for each component. No?
Yeah, there'll be a very high number of things, but in any case, we'll be able to search through them and let's see what happens.
Okay. So that's
Yeah. So number 3, the third thing that we can, like, the third addition that I want to do is this. See this one. So okay, so as we search this thing can only basically bound you to a certain. So in terms of time, it can only bound you to a certain growing interval, right? So for t equals 1, your interval is going to be this. For t equals 2, alpha will have grown, so your interval is going to be something like this. For t equals 3, it's going to be something like this, right? So your interval will have to grow with time like this, or they'll have to shrink with time if your alphas are less than 1, right? So what we want to add is we also want to add some bias to this, so that we can have some way to differentiate between a growing situation like this and a growing situation like this for different times, right? Because see, if your initial interval for t equal to 1 is this and you don't have some bias, then your next interval will have to be something like, if your initial one is something like this, and you don't have some bias, then your next one has to be something like this if it's just some alpha times t, right? So if this is alpha times 1, then alpha times 2 has to be this, and alpha times 3 has to be this. So instead, we are going to say, okay, alpha times something plus some constant b, right? So that we can say alpha times 1 plus b is this, and then alpha times 2 plus b is this, and so on, right? So to be able to express these sort of things, what we're going to do is we are going to bound. Okay, so maybe I should copy this. So we are going to have bounds on them as we had before. Sorry. And we're also going to add biases to this bound. So instead of, in some sense, instead of bounding C, H, F, and these things, we're going to bound these things minus some bias, and this bias is going to be a parameter. So then your thing begins to look like this, where you have J and some C's, and you have T minus 1 times alpha Lj, and plus some B is less than equal to Cj, is less than equal to T minus 1 times alpha Uj plus some B, right? So this is your invariant structure, and then your parameters is going to be these alpha Lj dot dot dot, beta Lj dot dot dot, gamma, and so on for each one of the, so this is say for C, H, this is for F, and similarly you have a set for I and O, and you'll have similarly this entire thing for the upper bound side. So you'll have this entire thing for the upper bound side.
But for alpha, there'll not be upper bound, only for
yeah, no, so for each one of them there'll be an upper bound and a lower bound.
Okay, everything. Okay.
And so you'll have upper bounds.
Okay, so this yeah, go ahead. So that I understand. So let's suppose,
and then you'll have these
if this turns out to be too complicated for them. Okay, is there a simpler, maybe we don't have to decide on that right away. Okay, somehow.
Yeah, I think we can. So that's why we can stop at
as a backup some more simpler, simpler versions of these things with fewer parameters. Let's think about that. Okay, so yeah, so that can already be changed. Yeah.
Yeah, and I mean we can always go back to here or here or here if that turns out to be simpler. But I don't think the number of parameters, like once the code is there, I don't think the number of parameters here might not like become that hard to deal with, because it's just some binary search over all of these, right? But let's see, we can discuss that later, sir, right? Yeah, so this is going to be this structure of this invariant. Now coming to the binary search, so binary search for one thing is clear to all of you, right? So if you have just one
parameter, it's clear.
Yeah, for one parameter is clear. So that for each parameter, so I'm now going to call this
I
generic
think they'll have to
parameters
answer that.
alpha
So
test.
for one parameter, it is clear, isn't it, you guys? That's what is used, because that one parameter, assuming that it takes a range of value between -m and +m, how you do, the search for the most optimal one in that range, okay, to get an inductive invariant. That's what figure 1 in the paper, the algorithm in figure 1. Okay. Any question on that? That's. I hope it's clear. Huh?
Hello.
Yes, guys. There.
Yeah.
Okay. Yeah. What you should recognize in that algorithm is, see, given a particular invariant with all parameters instantiated, invariance check involves one call to one SMT or ReLU, one SMT call, either Z3 or ReLUplex. Okay, that is the query for the inductiveness check. Whereas when you do this binary search, obviously it involves a number of calls. Okay, so you should be aware of that, and therefore the hope is that your initial experiments that you're doing right now with Amaya, with Z3, and pretty soon with Devjit and Harsh with ReLUplex will make a single check query, practical enough that you can actually make the search with multiple calls. Okay, so that's why making some progress with ReLUplex and Z3 for a single thing, you can of an invariance check is important. So hopefully you will have some positive movement by next Tuesday on that. So that then after that, implementing this is just one layer of programming. Okay, go ahead.
Yeah. So basically, if you remember in the binary search for each for the one parameter, say we had some parameter alpha, we had some lower bounds and upper bounds of the range that we were searching, and we were tightening these lowers and upper bounds and upper bounds, right? So we had some L alpha U, right? And we're tightening this L and U in each iteration. We're either tightening L or U and slowly zoning in on a particular value of alpha. So here we have multiple parameters. So we have multiple such LIs and UIs for each one of these. So I'm just going to say the parameters are, say, some alpha is, right? I'm using a slightly different notation now just to make things a little cleaner. So we're going to have LIs and UIs, which are going to be some ranges bounding each alpha, and we're going to slowly zone in on a particular alpha for each one of those parameters. So initially, LI is going to be some large M, UI is going, some really small minus M, UI is going to be some large M. And then we slowly use binary search to tighten each one of them and zone in on a region or on an alpha, right? Now, if you remember, the zoning in for the single parameter case, the zoning in was guided by this counter example, right? So we had this situation where if you have counter example to induction, then you would weaken it, right? So you would weaken, and that it looks like moving the Li up or moving the L up, right? And similarly, if you had counter to proving the property, actually, so counter to, so if the invariance is not does
is,
not prove the property.
it's too weak to prove
Yeah.
the proposed property. Yes.
Yeah, so then you need to strengthen. So that looks like moving U down, right? So now how does it change? How does this framework change for us? So now we have LIs and UI. So the first thing is, if you get a counter example, which of these LIs, so you need to tighten something. So if you say we have a counter example to induction, you need to move some LI up. So we know that we'll have to move some LI up. And similarly, if we have a counterexample to proving the property, we need to strengthen. So that looks like that is always going to look like moving some UI down, right? So which one of them should we choose? So choosing the I, it becomes key. So here's what I propose. Basically, the counterexample is going to be some point X. And this point is going to violate. So if you remember, our invariant was a conjunction of a bunch of these constraints, right? So it's going to violate some of these constraints. So it's going to violate some of the constraints. In each constraint is basically a bound involving an alpha and a B, right? So if you remember, invariant looks like this. So invariant is bound on some based on like this. So X is going to be bounded either above or below by some alpha I times t minus 1. And there is also going to be some bias here, right? And each one of these is bounded up by LI, UI, and so on, right? So, okay, just to make sure, these are different LIs and, oh, sorry, this will be U, right? And similarly, you'll have UBI, LBI, right? So you'll have different upper and lower bounds fixing the ranges of these, and we're going to tighten this as we go on, as I've been saying. So the invariant looks like this, and then the counter example is going to be some point which violates some of these constraints, right? So we pick one violated constraint. That is, we pick an I corresponding to a violated constraint, right? And then we are going to tighten bounds of that I, right? So now what we have is we have picked one particular I that, so we have picked one particular I naught, let's say, and we have this sort of a bound. And we want to tighten the bounds on this one and this one, right? Now, between these two, we are going to choose randomly. So choose between alpha I naught and beta I naught randomly. Right? And tighten that guy's bound. Right? So this is basically going to be the way in which we choose which I to tighten, and then we tighten it based on this framework. So so in some sense, I've written this, or let me just write it in the next page. So this is going to be 1 over here. Or step 1 is going to be use 1 to pick I naught, and then step 2 is going to be tighten bounds for I naught using 2, right? And you're all doing this based on a particular counterexample. This one is your 2. So essentially, after your set query, you have you'll have some counter example. This can be a counter example that comes from either your induction check or the check of your property. And then you're going to, based on that counter example, you're going to use 1 to pick a particular I0. And then based on the I0 that you've picked, you're again, based on where you're getting the counter example from, you're going to use 2 to tighten their bounds for that particular pick I0, alpha or B, and you tighten the bounds for that particular alpha I0 or B I0 as you have picked in step 1. So this is basically your thing. Now there are some, so before I, because I don't have much time, I'll just say this. There are some ties here. So the ties between, there can be ties when you have multiple such I0s. So then you break the tie by, so for example, you can violate many of the above bounds, right? So in that situation, you'll have multiple I0s that you can pick. So tie between I0s you can have, and then you break it by using this particular ordering. So you're going to choose C first, because we expect C to be somewhat stay the same across multiple iterations because it's a long-term memory. So you're going to choose C first. And then we're going to choose one of F, I, and O, because we expect these to put constraints on C. And then we are going to choose H. So this is going to be an order that you can follow to break ties. Within this, if you have more ties, you can just choose something that is random. So within this, right? So for example, if you have multiple I0s, so some of them are violated here, some of them are violated here, and some of them are violated there. So you have multiple I0s violated here, here, and here. You're going to, firstly, since you have I0s here, you're going to only focus on these. And then between these, you can randomize. If you don't have any I0s, any violations involving the C bounds, then you next focus on the FI and O bounds, and then within them, you randomize. And similarly, if you don't have any FI O bounds, only then do you focus on the H bounds, right? Yeah, so is this clear? Did I go too fast? I'm sorry if I... Hello?
Yeah, it's
So
clear.
what I propose is that, Diganta, you will, since you've written most of it, of course, you will upload this. You can actually put this into a document, okay? Just the algorithm, okay, and then publish it. So then they can, that way they can review it and then ask any questions. But before that, so anything else? So we'll have to wind up in 2 minutes. Okay, so if you have anything remaining, you can explain or take it.
No, I don't have anything on my end. I'll clean this up. I'll clean this up a little bit and post something a little bit more detailed, maybe. So then you can take a look at it and ask me. I'll also post this one itself as well. I'll post this one immediately. It'll take me some time to write down a more cleaned up version. And one thing I want to say is regarding, this is different, but regarding Reluplex, you will have to build it, Harsh. I'm sorry. I'll give you some instructions and you can call me if you have any problems.
Sad, but okay.
Yeah.
I had a question.
Go ahead.
So I wanted to know if you could save the results of the SAT solver or something like that, so that you can just show it later.
To show it.
Yeah, for example, Z3, is there an option to save it or something? So that let's say if computation takes 5-10 minutes or something, and you just want to show the results, and you want to present it somewhere else. So is it possible to save the state of?
Can you not dump your run to a file? I mean, that's all there is. I'm not sure if there is anything else that is.
Yeah, are you saying the internal state of the solver or just the result produced?
Output.
I mean, the result would have some kind of proof, right? So with that, the proof.
Yeah, so that and the proof that I think you can dump it out. I think you can get a proof out of Z3.
See, let's just say, what do you mean by proof? See, I can see the output it produces is, I mean, the run. Okay, so you type assert, okay, maybe with push and pop, and then there is a check, SAT check. Okay,
Right.
that then you'll either give unsat, or if it is sat, it gives a model. Okay.
Right.
Now, those things can be obtained using a dump. Okay, and then you could filter it out with removing junk and so on. But that does not give any proof. The output automatically does not give any proof.
Okay. No, I mean like proof for unsat. For SAT, it is clear that you get a model, but for unsat.
Yeah, for unsat, right now in the output, it doesn't automatically give you any proof. You will have to get some unsat core or something like that. Okay, there is an additional, a different command that you will have to use. But not sure, if you would want to actually, if either you or me or us want to inspect that, unless you want to use it for some purpose. Okay, you can, I think, get. For SAT solvers, these unsat cores are producible. Then you will have to use some command to get an unsat core. It will give some subset of your original set of clauses. Okay, that first you have to figure out what the command is, and I think it's unsat core. Okay, and then just like get model, there is some command for getting the unsat core. There also it will print. And so everything will be in the dump. Now, I don't know if there is anything else, any other utility command that Z3 or Reluplex provides in terms of proofs. Now, for Reluplex, you know what the internal state is. You don't mean the internal states. The internal state could be a lot more complex. Okay. In the case of,
I just wanted to to make iteration faster so that you could just load it later and it would get its results faster or something like that.
But by what? By turning some knobs?
No, not knobs. For example, let's say you have
one iteration to the next one, you would use it, is it? That's what you're saying?
No, iteration in the sense, not as in I mean testing iteration, like me iterating on the program. Not as in the solver iteration.
I understand. Yeah, that's what, by iteration, that's exactly what I meant. So from one unwinding iteration to the next unwinding iteration. That's what you mean.
No, I meant like iteration in the sense that I create some code, it works some okay-ish, and then I make some optimizations on that code. In that
yeah, my own this thing is okay. I don't know. I mean, that is something that needs to be looked at. So we have not gone through such details. So right now,
I mean, the idea was to load it later so that the SMT solver does it a bit
load
faster.
it later. So you can start from where you left off from the previous thing. That way.
In the sense that, for example, there is some stupid error that I made in the program.
Yeah, I understand. I understand what you're saying. No, yeah. But I think, but that's where the pop and push and pop can help you, no?
Yeah, but I don't think that those states can be saved to a file.
So that the next time you come, you
because
start from that. Oh, that may not be possible.
Yeah, you can pause the execution of the solver, or you can do incremental calls and such. But once you quit the solver process, all the internal learned clauses I think are not saved anywhere.
Yeah. So what you're saying is to save the internal state as a binary file, and then you upload it so that next time you come. Okay.
Yeah, that I think could be the interesting feature request for Z3.
I know that will be. I'm sure that there are things for very hardcore developers and so on. Probably they do that.
Right.
They have that feature, but whether they give that as as part of the standard utility, I really don't know. Yeah.
I mean, it doesn't sound like really hard to just store the learned clauses.
But there are issues, no? I mean,
There could be a number of issues. Like, I mean,
engineering issues.
so imagine that they like you won't have a learned clause. Like you'll have a complicated data structure with internal references and such, right? And those
Right.
references are pointers. So the pointers are, of course, they're bound to a particular
mean,
location
like,
of memory. Like
instead
it
of-
depends on what memory allocation you've gotten in that run.
Hmm.
So then you can't not use pointers during the run, because that would mean that things will get slowed down if you use fat pointers or something like that. So then what you have to do is you'll have to, when you save, you'll have to somehow keep track of all your pointers, go over them and convert it to some references, some other form of reference that can be saved and then loaded back.
Hmm.
So-
Maybe like you just, I mean, like I was thinking that some API would give me a list of learned clauses and then store them, and then next time just add it to the problem.
Yeah, I know, but see, I don't think the learn clauses are stored like, in some sense like Z3 ASTs internally, right? It will be like much more complicated and much more compact representation, right? And it will probably only be handled or manipulated in that compact representation.
True.
So yeah, then what you would, if you don't want to dump that binary out which has got the pointer issues, then what you would have to do is you'll have to write something to convert that to an AST like representation and save, and then while loading, convert that AST like representation back into that. And there can be some theoretical and or practical issues there depending upon things.
Yeah, there might be. I wonder
Hmm.
if there is a routine wherein if it dumps it as in SMT lib format, okay, into a file, all the learned clauses and so on.
Yeah. So that's what I'm saying. That,
Then
like,
you may be able to.
yeah, but what I'm saying is that
so-
if it's not there, it's not trivial to add it in. Is basically.
Yes.
Mhm.
I'll see. I mean, I don't know how to search for this over here, but I'll.
No. Yes.
Yeah, maybe I'll ask on somewhere if some people knows, like on Stack Overflow or something.
Yeah. So since we have to wind up, so I hope it is clear for each of you, Maya, and what we want to see by next Tuesday, the experiments that we want you to do. So, I'll reiterate it again. So, Maya is experimenting with Z3 in the non-linear version. And Harsh and Devjit, we want you to, the two of you, to collaborate to come up with a version of the network, the linearized version for ReluPlex, and run it on ReluPlex to check some simple property. Okay, you can choose the property. And both of you, I want you to do some, make the query for invariant inductiveness check, and then check for some simple invariant that you propose. Okay, so with say, in the simple template, so h is less than or equal to some 3 times t minus 1. Okay, so do something. Okay, and c is something like that, and c, and then use that invariant to make the invariant inductiveness check query, and then ship it to ReluPlex and Z3 in each of your case, and then see if it produces some result. Okay, so that's what I want you guys to do, because if you did that, then at least one level of experimentation we'll have feedback on. So how successful, or even how much progress you can make on task 3 very much depends on that. Okay, because task 3 is just a repeated call of inductiveness check. Okay, with a little bit of extra stuff added to go from either strengthen the parameter or weaken the parameters. Okay, as per the thing. So by Tuesday we'll have an idea. We'd like to get an idea through your effort to see if one inductiveness check query can be checked on. Yeah.
Hmm. Okay.
Yeah. Also, Hers, if you're worried about installing Marabu, you can call me. We can do it together on Zoom if you think
Okay.
that's.
Yeah, I'll try to do it. Like if I'm not able, I'll give you a call.
Yeah, sure. So yeah, I'm available today in the evening. If you want to do it like soon enough, because Tuesday is
Hmm.
not very far.
Oh yes.
Yeah.
Yep. I'll try to do it right now. Like.
Yeah, just follow their README.
Hmm.
It's mostly there. Like yeah.
Okay.
Yeah, I'll upload the video as soon as we do. So you can, Diganta will clean up what you wrote into some, so that algorithm will be uploaded. And I'll upload the latest version of the task descriptions. Okay. These three things will be done. Okay. Thanks for your patience.